welcome to this class. This is the second week class. So basically, we're going to go through the first chapter of your textbook. And in my handout, I say this is the chapter 0, okay? Because this is pretty much what you have learned before in the electromagnetic wave. And so we're going to go through this quickly and finish up in this week, okay? Just to get the clear concept about the electromagnetic wave. All right, so when you have a material in space, and then the material is going to respond to the electric field or magnetic field of your excitation. And this excitation could be just from a radiation source, like an antenna like this, okay? And somehow, when I have a radiation source, for example, this projector, coming onto this screen, what will happen? The electric field inside the lights is going to pull charges on this screen. And then whatever reach your eye, in fact, is the radiation coming from this screen. It's a re-radiation of the excitation, okay? So it's just not a pure thinking of like a reflection of something. It's a re-radiation process. So whenever we deal with light going through material or reflecting from a material, we need to look into a lot of antennas on the material or inside the material. And this is described in this term called P, polarization density vector. So polarization density vector basically is the density, volume density of the antennas inside this material. So imagine that you have a lot of antennas right here, and then doing radiation. Therefore, your eyes will just perceive or will see this screen. Okay, that is because of a lot of radiation antenna coming inside on this screen, reaching your eyes. And this is described by this term. And this excitation coming from this term, electric field, will pull the dipoles. And then all the dipoles, the density of the dipoles is described by this term. And there's a proportional factor. So this is the physical meaning of the polarization density vector. Okay. So think about whenever you see this, you imagine that in space, in a material, you have a lot of antennas, and there's a certain density of the antennas generating radiation for your applications. All right. So if you put this into the mass equations, then you can generate this inhomogeneous wave equation. On the right hand side, this is the antenna. Okay. On the right hand side, this is the antenna, and this antenna, this density of antenna is changing over time. The magnitude of it, the amplitude of it is changing over time. And the second derivative of this polarization density vector generates a wave in space, propagating in space. And on the left hand side, this is going to be the homogeneous wave equation. On the right hand side, you have excitation. Okay. So this is how we interpret this equation. And I haven't told you why we call this wave equation, because when you solve this expression, this differential equation, and you start to see this electric field, in fact, moving in space, and that's why we call this the wave equation. So let's come to a little bit more about dipole. Okay, a dipole by definition is two opposite charges separated by a distance. We call this electric dipole. And for a magnetic dipole, it's different. It's some sort of current going around some small area. We call that is magnetic dipole. But usually we look into electric dipole. And I told you that because the magnetic force require a motion, a fast motion of charge. Otherwise, you don't feel the magnetic force. So in optics, we pay much attention on electric dipole, because a charge does not have to move to feel the force, okay? And so this is the electric dipole, two opposite charges separated by some distance. But the charge is neutral, okay? This charge is neutral, you have positive Q, and then you have negative Q. The total charge are 0. And that is how we deal with this real world, right? Everything in the real world is neutral in charge. Okay, and then in fact, if we look into this material, the two opposite sign charge are separated with some distance. So we are looking into the real world, except that we just isolate one small part of it, and then look into this so-called electric dipole. And this electric dipole can produce radiation if this charge oscillates with time. Just like if I have an antenna, if I separate charge, positive charge and negative charge here, and then in the next moment, I move this positive charge downward and this negative charge upward, then the charge is going to oscillate on this antenna, and then it produces radiation. Okay, and later we're going to describe the power flow of an electromagnetic wave based on the so-called Poynting vector. And we haven't talked about this yet, but I'm sure that you learned about this from the electromagnetic wave class. Okay, and it tells you that the power flow of an electromagnetic wave is along the cross direction of electric field and magnetic field. And from basic mathematical rule, you know that the power flow direction is going to be perpendicular to the electric field direction and magnetic field direction. Okay, so this is sort of a very basic, quick interpretation about the flow of the power along certain direction. Okay, so important thing is that this power flow is going to be perpendicular to the electric field direction and the magnetic field direction. Okay, you tell me which direction of the electric field for this electric dipole. Well, if you have a charge oscillating along this direction, you are sure that the electric field direction is along this direction. Right. And according to this very simple relationship, you'll be expecting the strongest radiation is going to be along the 90-degree direction. So this is the electric dipole radiation pattern. We call this an antenna pattern of an electric dipole. So imagine that you have an electric dipole oscillating like this. The strongest radiation direction is going to be along the 90-degree direction. Okay. And then if you deviate this angle away from this 90-degree direction, the radiation intensity is going to drop. And if you look into the radiation direction along this dipole axis, you see no radiation. Okay, because it violates this rule. All right, is there any question? So this is the more or less common sense to you now because you have some background in electromagnetic wave, right? Any question? Sure. This is good, right? Easy. All right, but if you look down from top, then the radiation pattern becomes a donut. Therefore, because you have the axial symmetry along this direction. So when I say axial symmetry, this means that if I'm facing this axis, I look into this direction, it's the same as I look into this direction, because this is the axial symmetry. Therefore, the radiation pattern is going to be a circle if you look down from the top or from the bottom of this axis. Okay. So this means that if I have an antenna like this, which direction would you expect to have the strongest radiation? Yeah, which you knew it is along this direction, perpendicular to it. Okay, and then along this direction you see no radiation. And when I talk about this, I like to show you that if I have a cell phone and I hold it like this, my brain is going to receive a lot of radiation. But if I hold it like this, then I don't get. Well, depending on how the antennas are. Yeah, how the antenna is oriented. Okay, but most of people in the old-fashioned walkie-talkie, if you have the old-fashioned walkie-talkie, Antenna is just like this. Okay, because the person that engineered the designed the walkie-talkie did not come to my class. Right. So now you know that if you know the fundamental part of this, you can have invention, effective inventions. So this is the dipolarization pattern, and then we're going to come back when we talk about Bruce angle. Okay. The Bruce angle phenomenon is closely related to this dipolarization pattern. All right. Now, if I have a wave inside material, and I just want to see how the electromagnetic wave will propagate, then in fact, I can move the right-hand side into this plot and rewrite this conductivity. Okay. Previously, you have this expression, but in fact, you can move this term into this term because you have this relationship. The polarization density vector is proportional to the electric field, and we don't talk about the nonlinear part. Okay, so we cross out this in this class. But then with this relationship, you'll be able to move this plot into this plot, and then eventually the dipoles in the material is going to affect the propagation of this electric field. Once you do this, and this is wave equation, then the speed of the light is going to be affected by a refracting index. That is the square root of the relative conductivity. So we'll be combining this with this, and as a result, you have epsilon equal to epsilon r, epsilon 0. That is equal to 1 plus chi e epsilon 0. And then you have a u in your textbook. It's written like v, the same. That is 1 over square root mu epsilon. Okay. So you see that the dipole response affects the speed of the light inside a material. But this is reasonable, and it's quite intuitive. Why? So you know it, right? So if I'm in free space, I can move really fast. But if I try to walk into this array of table, and I interact with it, I deposit energy. Energy deposit process takes time. Do you agree? If I need to fight with you and go through the array, Li Xiaolong is supposed to be very good because Li Xiaolong's English name is what? Yeah, Bruce Lee. Yes, you adopted his name. All right, so you must be very, very good. If I want to walk across this aisle, it's good for me to take time to go through it, right? So if you send a wave, if you send a laser through some, I have toy box. If you send a laser through, for example, if you send a laser through this, this is going to be taking some energy from this laser because I have electric dipoles inside. And then the laser, when this laser going through this block of acrylic material, it's going to slow down. And the effect is described by this epsilon. Okay. So now, this equation just tells you that if you add this epsilon, the dipole response to the wave equation, overall, the speed of light is reduced by a factor n. This n is called refracting index. This n is equal to square root of epsilon r, and we call this refracting index. And in optics, we talk a lot about refracting index, and that the origin of it is the response of the dipoles in the material. All right. Any question? Come on, say something. No question. Good. right? Wave is a very strange thing from my point of view. For many years, I worked with wave, but for many years, I'm still thinking about it. Okay. Well, wave is the magic phenomenon. When I want to have to do something in Kaohsiung, or if I want to do something in Athens, I need to take a flight to Athens, right? I need to physically to be there to do something. But wave is something that you don't propagate material, but you propagate energy, and you can do the work. It can do the work for you. Imagine that you come to Taiwan to study for one semester, and you are physically here. But in fact, today, you don't need to be here, because 2 weeks later, I'm going to go to Sweden, and then I'm going to deliver my lecture through the internet. And what is being delivered from Sweden? In fact, it's a wave, energy propagating through some wave to reach you, and then my messaging, my information can be propagated to you. And I know you start to smile that, hey, professor is not in the class, then I'm going to have a good time in Taiwan, but no way. I'm going to try to catch you through the internet and then start continue to talk to you and put you into sleep, perhaps. Okay. But so this is the major thing from my point of view. If you have a rope like this, and then you give a perturbation, just kick it, then you have a small bomb. This small bomb, in fact, will propagate with some velocity. And then when this bomb reaches the end, it could refract. It could also transmit. And effectively, you have energy going back and forth on this medium. Okay. So a wave is something that the energy propagation through oscillation of an amplitude, but the medium does not propagate. Okay. So and this propagation, the phenomenon is described by this equation, and that is why we call this wave equation. Okay. It's a function of time and also space. Don't forget that this del, the Prussian operator, basically is the variation of something over space. Okay. So you have the variation. You take the variation of the amplitude over space and over time to describe the wave phenomenon. And this is the amplitude. It's not a material. It's not a material. It's the amplitude of something. Okay, it's the amplitude of the wave. So this psi, this C can be written into the electric field intensity, electric flux density, magnetic flux density, magnetic field intensity, or even voltage or currents in the transmission line. Okay, so this equation is so universal, and then we call this wave equation. And the solution of this is called wave function. All right, so this is a quick review. When we talk about wave, it's easy that you just throw a rock into a pond and you see the water wave move away. Okay, and in terms of the method of excitation, we sort of categorize the wave into the most three most common kind of wave. One is plane wave, one is spherical wave, and one is cylindrical wave. The reason we categorize the wave into these three forms is because that is easiest for us to analyze. For however more complicated wave can be synthesized from the superposition of these three kinds of waves. Okay, so we are not limiting our understanding of a wave by categorizing the wave into these three kinds. But just because mathematically they are easier to be written and then to be analyzed. And then for however more complicated wave, we can just use the superposition using Fourier analysis to synthesize them. Okay. For example, very quickly, I just show you that a laser beam. This is a laser beam. ooh, this laser beam is nothing like this, it's nothing like this, it's nothing like this. Why are we talking about this three kind of wave? Because I can use, for example, a set of plane wave to synthesize this laser beam. Okay, and this belongs to the knowledge about the Fourier analysis. Okay. All right. Any question? So quite often that in the textbook or in classroom we talk about ideal situation, but in real life nothing is ideal. But then, in fact, once you know the physics of ideal situations, then you can extract the key point. But then you can use the fundamental thing to synthesize the real world application. So this is the way we learn in the classroom. Okay. Well, imagine that you have a point source. You have a point source in space. Well, what do you mean by point source? Well, when I say point source, you say, hey, that's going to be just like this. We call this a point in space. But in fact, when you come here, you see, hey, this is not a point, this is a cylinder. So when I say a point source, that is subject to the location you view it. Agree? Right? When you sit up there, this is a point source to you, but from a point of view, no way, this is a cylinder. So same thing, this is the wave coming from a point source. And if I view this antenna from 1 kilometer away, this is the point source to me. So if I do my application 1 kilometer away, this is a good approximation. Okay, so this is how we learn the basic physics and then put it into application. All right. So spherical wave. Well, this solution has a form like this. It's a function of time and space, but the argument is always like this. In your textbook, it's written into this. R is a position, T is time, V is the velocity. And in this set of the slides, I extracted from some engineering textbook. The velocity is written as u. The important thing is not a symbol. The important thing is the physics. Okay. In your textbook, argument is written like this: r plus minus bt. But it's the same. You can write the t plus minus r over u. The same thing. Okay. It just tells you that the wave function has a dependence of this argument. All right. And for spherical wave, the solution of the wave function is further divided by r. It's further divided by r. Why? The intensity of the wave is it depends on the square of the amplitude. Okay. What do we mean by intensity? All right. Intensity has a unit of watt per square meter per unit area. All right. Well, let's say intensity. It has a unit of watt per square meter. This is the MKSA unit. You know it, right? And power has a unit of watt. Right? And then this is proportional to the square of the amplitude. When you do a surface integration, across the space integration over some volume, okay, some volume, do a cross surface integration, it gives you the total power. And this integration can be done at this location. It can be done at this location. R1, R2. The result have to be the same. If this is vacuum or some material without any loss. So we call this power conservation or energy conservation. Do you agree? Right? If there's no loss in this material, in this space, then the surface integration, no matter how I integrate over S1 or S2, I should get the same results. So think about that. If I have a intensity that is proportional to the square of the amplitude, and this surface is ds. If you have in the spherical coordinate system, this ds is going to be equal to what? R square the solid angle, right? This is from the basic calculus. You know that if I do a surface integration in the spherical coordinate system, then this is going to be the R square and the solid angle. The solid angle here is equal to sine theta d theta d phi in the spherical coordinate system. Right. So this means that if you want to keep this as a constant, then you will be doing integration of like this, I proportional to now y square r square d omega. But this is the power is a constant over distance. It does not depend on distance. So apparently, this has to be proportional to R 1 over R squared. So this means that the C is proportional to 1 over R for spherical wave. That is why you have this 1 over R dependence. Okay, so everybody understand this, right? For cylindrical wave, the situation is the same. If you do this surface integration, your surface integration here is going to be equal to length multiplied with for cylindrical coordinate system, that's right, R, and then d phi. This is for cylindrical wave. If I have cylindrical wave here, right, there's a certain length associated with it. Let's take the length of it. And the radiation is away from the surface. The radiation is away from the surface. So you will be creating a surface, a cylindrical surface, to do this power integration. You got it, right? The surface is going to be a cylindrical surface. For the spherical wave, this surface is going to be a spherical surface. Alright, so with this, L multiplied with R and d phi basically is going along this direction. So this means that you'll end up having an amplitude that is proportional to the square root of R. To make this P independent of R. And that is why you see this strange factor here. Okay. Because the C square is going to be 1 over R. That will cancel with this R in this integration and make this P a constant. Easy. This is too easy for you, right? All right, it's good that when I say it's too easy, you need knock your head. So this is really nice. Is there anybody who has difficulty with this? All right, the difficult thing is this one, plane wave. How are you going to create this integration? Incredible. This is not a function of not a function of position, because this plane supposedly is huge. Okay, it just tells you that the wave propagating along z direction, and then this wavefront is a constant. So when you do this integration, it diverges to infinity. Okay, so a plane wave does not exist. But it's a very good mathematical tool for understand the physics, and also you can synthesize a laser beam just from this plane wave through interference effect. Okay, so a plane wave is unphysical but extremely useful. Well, later you're going to see how we're going to use complex notation to do calculation. And complex thing does not exist in real life, but it's extremely useful for calculation. Okay, so people created this plane wave. That is unphysical because when you do this, the power becomes infinite. But it's a good mathematical tool when you do Fourier analysis. Okay, we'll see it. All right, any question? Let's move on. A plane wave, unphysical but useful. So we talk about it. Why do you think it's useful? Because I can cut it. I can just describe the wave very, very well. Okay, the concept. Well, if I have a plane wave, when I say plane wave or spherical wave or cylindrical wave, in your brain, in fact, you are telling yourself, I'm looking into the wavefront. So those planes are the plane of the wavefront. I throw a stone into the pond, and then you see the water wave propagating away. What did you see? What you see is the wavefront. Okay, every wave has a wavefront. Without a wavefront, it's not a wave. So a wavefront is the most fundamental thing of a wave. You see this bump? What is it? It's a wavefront. You are looking into this point. It's one point on the wavefront. You're looking into this point. It's propagating. Nothing. There's no material propagating. Okay, it's the propagation of a wavefront. All right. So if I look into the wavefront, then I have this. Also the crust and also the trough, crust and trough, this kind of modulation of amplitude. Okay, and so that's assume that when you cut it, then you end up having this kind of sinusoidal variation of the amplitude. And this is the simplest and also the most useful way of looking into a wave, and we call this harmonic wave. We call this time harmonic plane wave. Okay, the wavefront is a plane, and then the oscillation of the wave follow the strictly the sine or cosine. Well, this can be sine or cosine because time and position are defined by you. You can always set your start time and start position. So this, you can write this into sine or cosine with some arbitrary phase defined by you. Okay. So quite often in the textbook, you could find some arbitrary phase written into this expression. Okay. You could see that, for example, some solution with some amplitude, and then this is a cosine omega t minus kz plus some arbitrary phase to start with. And sometimes people write this as sine. That is okay because time and distance are defined by you. Okay. So to simplify, I simply take out this. I just define that when t is equal to 0, z is equal to 0, you have the maximum amplitude. Okay, but you're welcome to put any arbitrary phase there when you define your coordinate. Okay, so given this, well, if you have this kind of dependence in time, we call this time harmonic plane wave. Okay. This means that if you just sit at one location, and then, for example, receiving a wave coming to you, the electric field is doing this kind of oscillation over time, because this time harmonic wave. Okay, and a wavefront is a constant phase plane. So when you look at this wave at this point, is a constant amplitude at this profile. And mathematically, it means that you set this argument to be a constant. So with this definition, you see that this z is a plane in space. And that is why we call it a plane wave. Okay, and this plane, this wavefront is propagating. If you do a differentiation of this position, you are looking into one position with respect to time, and you start to see velocity. And that is why we call this symbol as a velocity. Okay, more precisely, we call this phase velocity because we are looking into a constant phase point. And a constant phase point is a point on a wavefront. Right, correct? So this is the straightforward, right? All right, so so there's an oscillation period and also a spatial period associated with it because this is a function of time and space, so you can deduce the spatial period and also temporal period. A temporal period is that when the wave oscillates one cycle, then it completes one cosine or sine cycle. So put the temporal period here, and then set it into 2 pi. That is the period of the cosine function or sinusoidal function. Then you end up having a relationship between the spatial period and also the temporal frequency. The multiplication of these two is equal to the speed of the wave. And you have this when you're in high school. And in Taiwan, I think people, little kids in high school already try to understand this. All right? So this is very straightforward calculation. Okay. It tells you that the speed of the wavefront is the multiplication of the frequency of the wave and the spatial periods. And this frequency is the inverse. This frequency is the inverse of the temporal periods. Okay. So a lot of information, but those are something that we learned before. Well, in general, the wavefront does not have to propagate along z direction. It can be along this direction. It can be along this direction. It can be along this direction. So you can replace the z with the position vector you look into. Okay. So just replace this z with the position vector in the Cartesian coordinate system, x, y, z. So this is also the perhaps first year calculus, right? And then it define the propagation direction of the wavefront along some unit vector, along some direction, kx, ky, kz, and of course if you normalize it, then you can create a unit vector along this k direction. Okay, and then if you set, so you rewrite this wave function into this form, k dot r into this expression, and k dot r equal to a constant defines a plane. So this is also the from the basic calculus, right? K dot r equal to a constant is defines the plane, and so if you set the argument, if you set this argument to be constant, basically you'll be looking into a wavefront. So this defines a wavefront. That is the plane. And the propagation direction, when you use this to define a plane, the normal direction of the plane is along k direction. And you knew this when you studied perhaps the geometry in high school. Right? Remember, you studied this in high school or in college? This is in high school already, right? So you need to have certain background to move forward. So try to catch the fundamental parts, and then you can move on. All right, this is one thing that create a lot of confusion to students. Optics is sort of between engineering and physics. So occasionally you pick up the textbook from physics department, and then you could pick up a textbook from the engineering department. And then people use different symbols to write square root of -1. In physics, people like to write I equal to -1, and people like to write J equal to -1 in engineering departments. But basically they are the same. But people do not adopt the convention of the starting phase of a sinusoidal function. Okay. In engineering textbook, the sinusoidal function for the wave is written more like this: omega t minus kz, and cosine is a periodic function. So the same thing can be written into this: kz minus omega t, because it's a periodic function, and z and t is up to your definition. And then what happened is that these two in the real world are the same, right? Cosine theta is equal to cosine minus theta. So in the real world, these two are the same when you deal with signal processing. But when you adopt complex analysis, the situation is slightly different. Well, so we'll ask, why do we want to use complex notations? Well, just because it's easy to do calculation. All right, so let's continue to write. In engineering textbook, if I write this as a real signal, I'm going to end up having these complex notations. This is exponential j omega t minus k z. And then if I extract this temporal function, and then keep everything inside this, what we call phasor, then you end up having this result. Agree? In engineering textbook. Right? When you are in engineering school, then you get this. But if you are in the physics department, adopting this notation, and then you move this temporal part to here with exponential minus I omega t. You can still define a phasor. Okay, you can still define a phasor. And then whenever you look into a signal like this, and then you sort of remove this exponential minus I omega t from the calculation. But the reason we adopt complex analysis and phasor is that we want to take out the temporal notation, the temporal calculation, because the sinusoidal oscillation is already understood in the problem. But then, well, let's go back to this equation. Okay, we talk about this wave equation, but there's a spatial variable and there's a temporal variable. And people feel this tedious. If the temporal variation, the sinusoidal variation is already understood in this amplitude, then can I remove this temporal variable? And the answer is yes. You just go through the complex notation, and then you can remove this temporal variable to simplify the calculation. So people notice that if you write it into a phasor notation, okay, just convert this into a phasor notation, and this term or this term is always understood in the calculation, then I can simplify. I can simplify the wave equation. And that is a Helmholtz equation we're going to use. And that is a presentation you have to tell me on this Wednesday. Okay, don't forget that you go through the review process and tell me how you understand it. Okay. All right. So in your textbook, it described this a little bit at the very beginning, and then eventually adopt this notation throughout the whole textbook. Okay, so apparently this textbook is written by a person educated in the physics department. But do you want to adopt this or adopt this? It's up to you. You just need to be consistently write down your definition. Okay, if you adopt this in your calculation, and then eventually you obtain some results, and then you want to convert it back to the real world, you choose this notation. You don't start with this and then choose this conversion. Then it's going to be inconsistent. Okay? So if you start with this and then finally get some solution for your phasor, then you multiply with exponential j omega t and take real part to get the real signal. Okay? Any problem with that? No, right? So if you start with this from the very beginning, and then finally you have some answer for your phasor, and you want to convert it back to the real signal, you multiply this with exponential minus I omega t and take real part of it to come back to the real world. Okay, so this is just like you can adopt in the old time an IBM PC, or you can adopt an Apple, the Macintosh computer, and then after you have the result from your simulation, then you put it into your machine and then fabricate something for the real world. Okay, but you have a choice to use IBM PC, or you have a choice to use the Apple Macintosh, Apple computer. That is okay. And apparently, the way IBM PC calculating some problem is different from the way Apple computer will calculate, because the computer chips are different inside. So this is how I make an analogy for you. Okay? So is this good? So from here on, for this set of the analysis, I'm going to adopt this engineering notation. Okay. And then later, if I get any answer for the phasor solution, then I convert it back to the real world by adopting this exponential j omega t. And notice that this I and j are in fact the same. Okay, it's just the way you write the sinusoidal function differently. Okay, all right. Let me continue, because now I'm starting to adopt the complex notation, and it's a mathematical tool. Okay, it's a mathematical tool, just like you use different brain of the computer. That's it. Okay. All right. A phasor notation. A phasor notation, for example, if I have a sinusoidal function like this, okay, and then I can write into this complex form, take real part of this, and then if I knock everything except the temporal part into the front part, then I create a symbol I call phasor. That is the complex number without the temporal variable. We call phasor. Okay. So we try to remove the temporal variable from the calculation by creating the phasor notation. Okay. A complex number has real part, has imaginary part, and then with this polar form, this angle in this polar coordinate system, showing you a vector having an angle with respect to the real axis. This angle is exactly this angle. So this is the basic engineering mathematics you learned before. Okay. And with this, you knew also the summation and subtraction, multiplication, and division. And you just follow the rule to do the calculation. You found out that the polar form of the complex variable is very, very powerful. Why? When you do a division, the phase angle is the subtraction. When you do multiplication, the phase angle is the summation. apparently summation, subtraction are easier than division and multiplication. Okay. So if you care about the phase angle of some physical variable, then complex analysis is a very powerful tool. Okay. We'll take a 10 minutes break and then come back.